Good morning, young people. It's early Thursday morning. I'm trying to make this before I have to go to my meeting. So today is Solution Stoichiometry Part 1. We're going to try to figure out more about why solutions are made and then go from there, okay? So, solutions, what are they? They're homogeneous mixtures. They're homogeneous mixtures made up of two things. Those two things are a solute, the thing that's being dissolved, and the solvent, the thing doing the dissolving. So when we think about it, we see something like this where we have some sort of a solid mixing in with water, and that makes a solution because if it's soluble in water, it will dissolve. So what affects dissolving? The nature of the solute affects dissolving. So is the solute ionic or covalent? Is the solute a strong, weak, or non-electrolyte? All of those things affect dissolving and how that happens. So soluble or insoluble is important as well. The solvent, the amount of the solvent is important, the temperature of the solvent is important, and the type of the solvent is important. Now, we use aqueous solutions a whole lot. What does aqueous mean? Aqueous simply means that water was a solvent in the solution. However, you've probably seen at home you have something called the tincture of iodine. Tincture means that alcohol is the solvent. So iodine was dissolved in alcohol to make a tincture. So if you see tincture as a word in a solution, it's because it's got alcohol as its solvent base. But we typically use water. As a matter of fact, we call water the universal solvent. That's not completely true. It does not dissolve everything. It does not do everything, but water is the key to our lifestyle. It's the key to our life. And because it dissolves stuff, we call it the universal solvent, and we use it quite often. So what are the properties of water that make it the universal solvent? It has a high specific heat. It has a high heat of vaporization. So high specific heat means that it heats up slowly and it holds the heat once it's heated up. So that's why, in the summertime in the evening, you might get a fog over water because water is actually cooler than the air around it usually. And then as the air around it cools down and the land cools faster, the water's warmer, producing a temperature differential between the two and therefore creating a small cloud above the water. Okay, high heat of vaporization means it takes a lot of energy to get it to go into a gas. So we have a high heat of vaporization. High cohesive forces, it likes to stick to each other. All the molecules of water like to stick to one another. High adhesive forces, that means they like to stick to other things. So if we think about a graduated cylinder, water likes to stick to the graduated cylinder. That's why it makes the meniscus, because the water is adhering to the sides of the glass of the graduated cylinder. So these are all important properties of water that make it our universal solvent. The bonds of water are also important. There are two OH bonds that are polar covalent. What does that mean? It means oxygen has a higher electronegativity, so the electrons are more attracted to oxygen and spend more time there. This creates what we call a partial charge, as shown by the Greek lowercase letter delta. You see delta right over here. Here is the delta right there. That's what delta looks like right there. Okay, so this is what we're talking about. You see this oxygen. Oxygen is what we call an electron hog. It does not share electrons evenly. It wants the electrons more. So what ends up happening is the electron that is being shared by hydrogen and the electrons that are being shared here in this hydrogen get pulled to the oxygen more often. And what that creates is it creates a partial charge. So each of the hydrogens has kind of a partial charge of 1, and the oxygen has a partial charge of 2. We also notice that the bond angle here, now we don't know much about bond angle, but what we do know is that in a situation like this, the bond angle should be 109.5. But because we have these pairs of electrons that aren't being shared by anybody, they're hogging the space. So what they're doing is they're squishing that bond angle between the two H's about 4.5 degrees. Because, hydrogen doesn't have very many electrons, so it doesn't need as much space. The electron pairs take space there. So these are known as, these two dots right here on either side of the oxygen are the unshared electron pairs. And we'll learn more about how to do that structure a little bit later. The two unshared pairs of electrons cause a partial negative charge to be 2 delta, which means a partial charge of 2. I know that's a little strange, but basically what we're saying is this hydrogen and this hydrogen are both unequally sharing their electrons, so we have a partial -2 charge there. So hydration, what is hydration? Hydration means that water is able to hydrate something. And since opposites attract, the positive ends of water are greatly attracted to the negative ends of ions in crystal structures, ionic crystal structures. And the negative end of water is greatly attracted to the positive end of the crystal structure. So what we see happening is because we have this partially negative side over here with the oxygen, and we have this partially positive side over here with the hydrogen, that creates a situation in which the water can hydrate an ionic crystal very easily. So we get into solubility. So hydration is a little bit different than solubility because water can attract to these ion crystals and actually provide more to their structure and provide very pretty colors. That's what we call a hydrate. And that's a little different than being soluble. Solubility, sodium chloride is highly soluble, while silver chloride is classified as insoluble. Why is that? Well, it has to do with the hydration attractions. So the hydration attractions are greater in the sodium chloride than they are in the silver chloride. So that's why we have this idea of a hydration going on in solubility. So when the hydration attractions are greater than the crystal lattice attractions, that means the attractions of the two ions to one another that are all around in the lattice structure. Remember, one formula unit isn't what we see. We actually see several hundred formula units stacked on each other, and you'll see a picture of this in just a second. Okay, ionic compounds. Also note that the particles in ionic compounds are charged. They're charged ions. That means they have a full charge. They don't have a partial charge. They're fully charged. So we have to think about that when we're thinking about the attractions of the ion-ion, because if that attraction is greater than the attraction of that partial charge on that full charge, then it doesn't dissolve. If it is greater, then it does dissolve. So here's the picture that I wanted you to see. This is basically sodium chloride. You see the chlorine here, you see the sodium here. This is how we see sodium chloride. We see it as what we call a crystalline lattice structure. That means every positive is surrounded by a negative and every negative is surrounded by a positive. And so this is the attractive forces that we're talking about, the electrostatic forces that cause that attraction. Well, if water, the partial charge forces on water that you see here in this water molecule, if they are great enough to attract these ions away, then we will have solubility. So you can see what's happening here, right? So you see them coming on and they're trying to grab onto these. Well, the hydration attraction is greater for sodium chloride than it is for silver chloride. So you can see that the positive ends are next to the negative and the negative ends are next to the positive, and they're causing them to move away. And this is what's happening in that water as things are dissolving. So solubility has to do with the electrostatic attraction that's occurring between the water molecule and the other molecule that's there. And if there's no electrostatic attraction, it's very unlikely that there is solubility. But even if there is electrostatic attraction, if that electrostatic attraction of the water to the compound, to the ions in the compound, isn't great enough to overcome the force of electrostatic attraction between the particles, then we don't have dissolving happening. So, non-ionic substances. Well, water can dissolve covalently bonded substances too, like alcohols and sugars. These compounds contain OH bonds as well that are polar, just like those in water. And that's really key. When we have a non-ionic substance, if it has some polarity because it has an electronegative end somewhere, then we have the ability to dissolve in water. So polarity makes these molecules soluble as well, but it's different. Because these are soluble because of the polarity differences in the two, it's still an electrostatic attraction, but it's not the same as it is with an ionic. They don't dissociate completely. So we see here, we see this OH bond in ethanol here. This OH bond in ethanol has a polar end. So you see the negative end where the oxygen is and the positive end where the H is. So what ends up happening is the negative, partially negative O attracts to the partially negative H in the ethanol, and hydration is continued because there's an electrostatic attraction between those two polar covalent OH bonds, okay? So we can also see we have OHs in sugars like dextrose and ribose and sucrose. Anything in an ose is usually fructose, galactose, glucose, dextrose, ribose, sucrose. All of those in an oses, that means that they're sugars. So you're kind of getting a little bit of an organic lesson here too. So in non-ionic substances, the only way that they're soluble is if there's some polarity about them. If there's polarity about them, then the polarity of water and the polarity of them can help to build that electrostatic attraction that is then creating what we call a hydrogen bond and can then dissolve this substance in water. Okay? Fats do not dissolve in water. They are nonpolar, so there's no way for them to dissolve in water. That's why oil floats on the top of water. The words like, dissolve, like is very useful for predicting whether or not things will be soluble, especially in non-ionic bonds. If we know that they're not polar, then we know that they're probably not going to dissolve in water. It's very unlikely. If they have a polar proportion, it's very likely that they will dissolve in water. But on the AP test, when you're explaining this, that like, dissolve, like is not an explanation. You have to go back to the electrostatic charge attractions. The idea that you have a partial charge on oxygen that's negative, a partial charge on hydrogen that is positive, and because those partial charges would be attracted to each other, they create a hydrogen bond that then lets the non-ionic substance become soluble. Okay? So you have to be able to describe it like that. Huge point. There's a difference when we're talking about ionic substances because we know non-ionic substances don't ionize at all. There's a difference between solubility and ionization. Solubility is talking about the amount of a substance that will dissolve in the solvent. Ionization is talking about what happens when it dissolves. So ionization is the process by which the water hydrates these things, pulls those ions away, and creates ions within the solution. Solubility is describing how much of that solute will actually dissolve in the solvent. Okay, now we're going to be talking about the nature of aqueous solutions. Yes, aqueous because we always deal with water. So electrolytes, we need to know about this word electrolytes. Electrolytes are basically solutions that conduct an electric current. So we know that the more mobile and charged particles, that means the more moving and charged particles that are present, and the higher the concentration of ions in solution, the better conduction we get. That means the more conduction of electricity we get. So, and the magnitude of charge also matters. So if we look at this, we can have strong and weak electrolytes. Electrolytes are going to be ionic. You're not going to have an electrolyte that's not ionic. As a matter of fact, they're called non-electrolytes, and we'll deal with them in a little bit. So a strong electrolyte completely dissociates. We need to understand our solubility rules. We need to know what strong bases and strong acids are. We also need to understand that barium chloride is an ionic salt that completely ionizes into barium ions and chloride ions. Hydrochloric acid is a strong acid that completely dissociates into H+ ions and Cl- ions. While NaOH is a strong base that will completely dissociate. So if we see barium chloride here at the bottom, and then we see barium chloride here dissolved. Notice that there are double the number of chlorine ions. Why? Because barium has a 2+ charge, chlorine has a 1- charge. Okay, you see hydrochloric acid here. Notice the equal amounts of particles. And then you see NaOH. So you understand that they all completely dissociate in water. So they all release mobile charged particles that conduct electricity. So weak electrolytes are a little different. They do not completely dissociate, only about 1%. These are our weak acids and weak bases. And even some insoluble things do dissociate partially. So if we see there is our acetic acid, we see it's dissociating. We also see it's more covalent in nature, but it will dissociate and give up an H+ ion. We also see ammonia in water, and we can see that it is actually attracting to the water. So we see that there is some dissociation happening there. We're going to stop here for right now, and we'll continue this a little bit later.